A very good afternoon to everyone. On behalf of the Department of Chemistry, I extend a very warm welcome to all of you to our third lecture of the Centenary Year celebrations. Today we have with us Professor V.K. Singh from IIT Kanpur as our guest speaker and Professor Balram Pani, Dean of Colleges, as the guest of honor. I now request our speaker, guest of honor and the head Department of Chemistry to please occupy the dais. We will now inaugurate the session by lighting up the lamp. I request Professor Prasad, Professor Singh, Professor Balram Pani and the section conveners to please do the honors. Thank you, sir. I now invite Professor Ashok Prasad to please invite and introduce Professor V.K. Singh.
Today's Centenary Year celebration third lecture, Padma Shri Professor V.K. Singh, popularly known as V.K. Singh, Professor Vinod Kumar Singh from IIT Kanpur. Our guest of honor, Professor Balram Pani, Dean Colleges, University of Delhi, my esteemed colleagues from the department, and all my dear students, research scholars, master students, and all the colleagues and students who are attending this Centenary Year celebration third talk online. I welcome all of them to this talk. I am glad that Professor V.K. Singh, in spite of his very busy schedule, accepted our invitation to come to our department and give this centenary talk. In fact, he is not coming from Kanpur. He was in Bangalore before coming here. So he just, instead of going to IIT Kanpur, he dropped here just to bless us and give his talk in our department. We are celebrating centenary year It's a great occasion for all of us. Our Vice Chancellor, Honorable Vice Chancellor, always says that, university started in 1922, but we are lucky enough to witness this 100-year celebration. Many people came and went. That this 100-year occasion didn't come in their career, though they served this university, as much as they could do. So we are really lucky to witness this celebration and to have Professor V.K. Singh in our department to give this third centenary year talk. Just to inform Professor Singh that University of Delhi started with an Act of Parliament in 1922 only with the 3 colleges, and these 3 colleges were St. Stephen's College, Hindu College and Ramjas College. And there was only 2 departments, 2 faculties in the university, arts faculty and science faculty when it was started. Even the science faculty has only 2 departments, that 2, physics department and department of chemistry. And when it was started, there was no master's teaching in the department, only graduation teaching was there. And in the beginning, some 700 students were there, all these 3 colleges, different arts and science faculty departments. So it was a very meager start in 2022. And now we know that we have, had a long march from that time to today, and many great luminaries have served our university in this journey. So now the number of students is 6.5 lakhs, 90 colleges, and more than 20 faculties are there in the University of Delhi. So that is the expansion. It's really a big expansion. And it's a big lesson for also. So we know where we need to go. And university has already started preparation, sir, that where we will be when India will celebrate its 100 years of independence. So we have already started preparing for that. So with this small note about the university and establishment of our department, I will just give a brief introduction of Professor V.K. Singh to our students. Professor V.K. Singh is a distinguished Director's Chair Professor at IISER Bhopal, and for your kind information, in fact, he was a founder director of IISER Bhopal, and he bricked this institute from brick to brick. So that's a great achievement, and this is one of the best IISER at the moment in the country. And he is also holding Rahul and Namita Gautam Chair Professor in the Department of Chemistry, IIT Kanpur. He is currently the President of CRSI, Chemical Research Society of India, which is one of the best research society, organizes wonderful conferences and work tirelessly for the development of chemistry in the country. And he is also the Chairperson Governing Council of IACS, Indian Association of Cultivation of Sciences, Kolkata. Professor Singh did his PhD under the guidance of Dr. Sukhdev from Multichem, which was at that time associated with MS University, Baroda, where our Vice Chancellor was Vice Chancellor there for some time. So when the name of Professor Sukhdev came, I always remember him. He also gave a talk in our department when I was doing PhD. And when I saw him for the first time, I really realized that it's some Indian scientist is there with his dress and the way he spoke about the science and about the country. He is a great scientist. He is still, in his late 90s, and he did tremendously great work in synthetic chemistry, natural product chemistry. And at that time when I was doing PhD, Multichem, where he was director, was a big name. That was just like, when you hear about Harvard, it was in India like that at that time. So Professor V.K. Singh has been trained by Professor Sukhdev. After that, he spent 2 years in Canada as a postdoctoral student, and then he came to Harvard University to do his postdoctoral studies with a Nobel laureate, Professor E.J. Corey. All of you have heard his name. He has given a direction to the synthetic organic chemistry. He subsequently moved to, after his second postdoctoral studies at Harvard, he worked for a while in Neurogen Corporation in Connecticut, US, before he joined IIT, Department of Chemistry, IIT Kanpur, as an assistant professor, where he rose to the rank of professor. He works in the area of synthetic organic chemistry, especially asymmetric synthesis. His research work has been recognized with several awards and honors, such as Swarna Jayanti Fellowship, Shanti Swarup Bhatnagar Prize, and Padma Shri, which is not only awarded to a scientist, it is awarded to a scientist who does great job for the society, because it is a national honor. So he was also awarded this Padma Shri in 2014 for his work in science and society. In addition to this, Professor Singh has been elected almost fellow to all national academies, including the fellow of the World Academy of Sciences. He is editor of many important and which you every day come across journals. For example, Tetrahedron Letter, which is published by Elsewhere, Organic Letter, Journal of Organic Chemistry, published by American Chemical Society, and Asian Journal of Organic Chemistry and Organic Chemistry Frontiers. So all are the best journals which we use every day. As a founding director of IISER Bhopal, he was 10 years as a director of Bhopal. So he not only started IISER Bhopal, he bring IISER Bhopal to the level where it is today. So he bring this institute to the present level. He has also mentored IISER Beharampur. This is a IISER which was opened in Odisha, Beharampur. And he was also director SPA Bhopal as an additional charge, and the chairman of Board of Governance of NITTR Bhopal. He also held the additional charge of directorship of MANIT Bhopal and mentored Triple IT Bhopal. So you can understand that his administrative acumen and capabilities, along with his scientific achievements. And then I will also take this occasion to thank Professor Balram Pani, who has taken time from his busy schedule to come and to grace this occasion. And before inviting Professor V.K. Singh for the lecture, I request Professor Balram Pani to please say a few words and bless our department. Sir, please.
Thank you, Professor Ashok Prasad ji. Good afternoon to you all. On the dais, Padma Shri Professor Binod Kumar Singh, and my dear colleagues and student friends. Now, this is the centenary year. We just say in the past May 2022, we have celebrated the centenary year. From that, it is almost 1 month. Within a month, the chemistry department is taking the lead. That is the centenary year celebration. That is the lecture series. It is the third lecture series. And if this type of frequency will be going on, then definitely by the year end, we may cross 50. If in between, if it will be slowed down, means whatever the topic it is, that is the catalyst, you can put some catalyst so that if there will be any slowdown, then again you will be accelerated. And definitely, this lecture series will be more than 50. And if it will be so, then definitely the students, not only the postgraduate students, the research scholars, as well as the teaching faculty also, they will be benefited. Because such type of personalities, you just see, if you will find out the awards and designation of Professor Vinod Kumar Singh, it is almost one paragraph. From that, you can imagine means how means a big sorry he is. If such type of a big personalities will come to our university and to our department particularly, then definitely we all will be benefited. So it is not only the chemistry department, as a whole, the Delhi University will also be benefited out of that. Means it will be very much, means the lecture series, if some tips may be given so that the research scholars will take that one and may lead in that directions. So definitely such type of means, this lecture series or seminars or workshops may be carried out, and chemistry is always leading ahead with all the departments. And I will not take much time because you are agreeing to listen to Professor Vinod Kumar Singh, and he is here. And you know, means when I was the student, at that time I heard that particularly the IIT Kanpur, it is best in chemistry department. So that's why, means now the professor Padma Shri Vinod Kumar Singh, from the best department of chemistry, he is here. Now, right now, we will listen to him and will be benefited out of that. Again, I congratulate to you all, and I am also privileged to be here and congratulate to you all because you have invited me. Thank you.
Thank you very much, Professor Pani. May I request Professor Singh to kindly deliver the talk?
organic chemistry, they had only two elective in the department. One is total synthesis taught by E.J. Kore and asymmetric synthesis taught by Devarma. And that's where I learned little bit. Normally when you sit in a class, you don't have to write paper, learning is less. So the main learning came when I joined IIT Kanpur, when I started teaching. So what I want to stress upon, even if you do not know or do not understand it, you got to have passion and you should be willing to work 7 days a week, day and night. You can learn. With this, I will start my talk. Asymmetric organocatalysis. I'll try to finish my lecture in less than 47 minutes, because it shows 47 here. The Nobel Prize was given in 2021 and for the development of asymmetric organocatalysis. And the people who got Nobel Prize, they are actually both were born in 1968. You can calculate the age. They were 53 years old when they got the Nobel Prize. And every time I go anywhere, I say, in first 10 years, if you have not done any good research, it is very difficult to do beyond that. Not impossible. So first 10 years is very, very important. So whatever you want to achieve, young age you have lot of energy and you should work very hard. Don't worry about facilities. Sometimes people say that I don't have this, I don't have that. I think nobody wants to listen to your problem in life. People want only research. For example, IIT Kanpur did not have an MR for 10 years when I was from 90 to 99. No HPLC, no rotavirus. So you can see that. But it doesn't mean people stopped working. Publish less, may not publish very good paper, but some activity will be going on. So I want to stress that you should not waste your time when you are young. Okay? And once you reach 50, main time is already gone. Professor Ben List, who is a Max Planck, and David Macmillan, who is now Princeton University. And asymmetric organocatalysis means organic reaction catalyzed by small chiral molecule. Basically, instead of metal, organic molecule catalyze the reaction. Now, 20 years ago, Nobel Prize was given to these three gentlemen, Barry Sharpless, for Sharpless epoxidation reaction, and the paper he published in 1980 or 81, I don't remember exact year. And today if he published the paper, time is very, very stress upon work you do. Theory and no. So in my talk, I'll be first chirality. I'll be using these words very much. Chirality is yes, you are. That is why I have shown one. All these things are highlighted with color has nanomolar activity. The moment go to the other enantiomer, H at the top, you bring in carbon-carbon double bond, in other words, fatness. So that one. Getting the drug. By the habit, ibuprofen, like are in it. Prozol, so there are three ways. This industry is but talk about it. Yes. Here what? Take carbon, add in the get held on, generate a chiral center. Asymmetric 45. Asymmetric tower. All what happens? Have this dehyde 5 I have drawn in the back side. The front side I have a nucleophile which is the base to generate enolate. Then facial reaction happens. Face attack. The attack takes place from C phase. Get one enantiomer. Block one phase. Critical down. So difficult. Get the some For example, S in N2, R in N2. Energy difference between higher will be the what is in H? Here, ratio of these two isomers. For example, 99. Optical purity will be 99 minus 1 is some weight will be like I never like to quote their result. The real one. So these are the energetic. You have to get it, right? Local per mole. I also like to mention for a long biological catalysis. These are the method. So 2 slides about the chiral. This is part system but not in it. Pi box again, Nishiyama is the first one who used that Evans used extensively. Masamune Shinsai similarly again. That basic structure is same. Jacobson, this is the ship-based kind of. Had a similar ligand, organic chemistry member, has already further. Jacobson did, brought in chiral. Evans Corey used a similar kind of Corey ligand, and Kanpur we designed this similar to Nishiyama's ligand but having gem type. And then Davies, you recall, is also like a similar ligand, he had substitution. Chiral ligand you have, plus you have nickel, copper, magnesium. 2. Now I give you one example. Postdoc in Evans. Reaction, for example, is aldol reaction. Carbon. All silyl ether attack this carbonyl. This is the pipe of you can see 3-dimensional. What happens? Reaction takes place. Ester group, both the oxygen chelate very tight. Look at this phenyl ring blocking this ring. That has to take place at carbon. Space is open. Right? In other words, have a carbonyl compound lone pair chelate to the second is chiral. Tell what it does. Just I wanted to show you the one published by Evans. Biological catalyst. asymmetric. Without movement. Choline has asymmetric. Can high urea base. Conjugate acid of ligand was how was the first one to had synthesized this ligand to the metal we are using depending of the hydrogen. Acid like this one, strong acid, Bronsted acid, acid. Both the way it happens like this. Hydrogen bonds here is weak acid, then you have a weak hydrogen bond. Strong acid, the hydrogen comes to the bond. Have L minus, pair kind of. Here what happens is 4 electrons. That's very important. Now, intramolecular is all way back in 70s. Get intramolecular enzyme. So, that chemistry. Violent Nusselt. You can see the country. On where we are not that base NH by N methyl. The carboxylic acid you have ester. The 5-membered ring, 6-membered ring. Then Danishevsky has okay. Then in synthesis of erythromycin has helped to carry out this intramolecular. And you can see in enantiomeric excess this solve it. Label method. I have couple of slides from India that he had carried out intramolecular. Another one published the paper, but if you read the paper, I read it. Then intramolecular one. Third is without reaction. Third which was the differences. Out in the this published a paper. Paper appeared in year 2000. Barbas, talk in Barbas lab history. Barbas published paper in fact, Benlis was postdoc and also just joined. out aldol reaction, IST 86%. Macmillan again published 1000 carried out the reaction. Like to mention, got Nobel Prize. Now you can question, yet intramolecular was already helped on already. Here DMSO. That where I have summarized Benlist if this instead of metal he used hydrogen. Here so carboxylic acid is important. Activate this carbonyl group. Also there is a chelation that some 6 member trans. Then he how did lot of have summarized the final or how what he proposed kind of transition. How says hydrogen bond has that calculation. How also said there is a hydrogen bonding with H and depicted in this kind of fashion. But he had proposed Zimmermann tractor out this model called Zimmermann tractor based on Zimmermann. How what he said NH bond lower down the NH. Sorry, NH bond does not lower down. The other thing, amine carbon-carbon double bond is anti the carboxy. What he was trying? Carboxy. Cross carbon nitrogen. Then he takes 2 off. Case of aldehyde is accepted. RS is here kind of arrangement comes here, it will be anti. So approach is C, the theoretical, but I have just some action. Why to have ester reaction? So mechanism all reaction. I said this is it. Paper, the paper one. Our focus was all reaction. Trust me. Published a paper we had. Both the papers they introduced acid. They used to say to add water is reaction. I to add acid, otherwise have normal base catalyzed acid. That is the recipe. Per case, have to add any acid. Reaction goes there. About it. But the transition state we had proposed is bifurcated hydrogen. Can all be based on again. And what we have seen that gem diphenyl plays very important role. There is a non-bonding interaction. The next slide. Well, for method get difficult because formic acid he was getting mixture you dilute acid. Publish this our work. Here, there is a small the small thing it is. And size 70-80 gram. And there is a review also article on azole reaction done by list. Azole is nothing. Any reaction though that then is the argument. And was all correct. Get some of the dicyclo synthesis. You can see that from molecular Dol reaction percent. Slowly. L-proline has at pK value. pK value is high function. Pyrrolidine forms for can use nucleophile to get called a very good method. Barrier. Isoselective. Frontier orbital interaction. Normal Diels order reaction. Doesn't matter whether, for example, copper. There is interaction of homo of diamond. I mean electron, but the LUMO now it is. So the energy barrier is by the reaction. For this where the time, but reaction is the now. How do you activate the dinophile? Paper actually. Very important. Gates from basic catalysis help develop this. You have this dinophile. This acid who comes down here. Carry out Diels order reaction at minus 8 degrees. Yes, by S material. The facial selection. That can be base you have to activate the dinophile, chiral catalyst. From here, normal dinophile is like this, LUMO is here. Lewis acid, if you add LUMO, blend it, type. Simple, I mean, he also carried out this reaction. So now LUMO is somewhere closer to here. That is enough. Basically, it acts like Lewis acid. You can see the reaction. Now with this concept, the first paper, this imidazole we don't. You can see the dinophile and dine. So XO ratio was very so selective. First paper. Just come to the next. You can see it was initial. This unsaturated heat. There was LU. Here there was no E. Again this brought in phenyl group here. Brought here benzyl phenyl here. And this one gave the highest heat. Endo-exo ratio is also important, as then you get 25 papers are published and gave well, and those has been order chemistry. Normal. The way it happens ruthenium. Benzyl group blocks the top. Now dine is calculated by calculated the observed is calculated E and out. Very active. Yes, try this one. Then the key reaction is Diels order reaction. This is dyne. You can read this paper. I'll just tell you what is happening. Here dienophile. Here this compound. When you add in acid, protonation takes place here because the lone pair comes here. Protonation here, kind of on minium ion. Lone pair comes here. Here. And then same thing you can write in this direct way. Lone pair attacks here. Compound. This has been again. One more synthesis. Primer synthesis by word. There you have done the dyne by without arrows. If you look at good living group south, then what will happen? Then story is have aldehyde on you can have electrophile and this bit. One example of activated nucleophile. The computational model. Here you have enamine. Here you can see top is blocked by this. No activation. Not because that electron generate radical cation where you can have called soma. You can have nucleophile without like to mention the development physical work of Dahl. Because generic activity, the reactive is getting many